you for inviting me. So good afternoon, everyone. Today I would like to talk about one of my research topics, which is weakly supervised learning for autonomous cars, for autonomous driving. Actually, I've decided to include also some self-supervised methods. So basically, I want to just do I guess a very sort of deep dive, very quick deep dives into two methods that I think are a good sort of examples or things that people in this area are interested in, and to just basically just give you a feeling what can be done and what is currently being done in this area. So first, I think I want to show you some motivation. So So, in autonomous driving, some events or some things are rare, and some things are very rare. This is quite a common theme in this area. It's sometimes referred as a long tail problem, which basically means if you look at distribution, let's say of classes or anything, it would have a shape where the tail or the number, let's say, of instances is so decreases over time, and then in the far end you have instances which you may have only once or twice in the data set, and this is why it's called a long tail problem. As a motivation, I picked up this example. So this is an actual event in the UK. Maybe let's zoom it a bit. So imagine you're driving in a car, and suddenly this is for those who are not familiar with driving in the UK. This is a motorway, dual carriageway. So this is like an equivalent of our highway, and so it means it has two lanes both ways. And you can see in the right lane, there's someone driving his horse, or it's a horse carriage. Furthermore, again, this is in England, so actually he's in the fast lane, right? Because people drive on the left, and if you want to overtake the car, so he's actually overtaking these cars. And why I'm using this sort of anecdote is, this is a typical example of a rare event in autonomous driving, because it's not very likely that this type of event, let's say you have a autonomous driving assistant, and you want to detect cars, you want to detect objects to avoid. Of course, what is the chance that this type of event or this type of object is captured in the training set? So maybe let's just quickly look at how rare these events actually are, just to give us again some maybe estimate, and also this is a motivation for why the methods that I'll be talking about are actually important. So first, let's take a look. This isn't a made-up stuff, or this isn't an artificial scenario. Let's look at Tesla. This is Tesla, I think 2021 model, and let's see watch closely the dashboard of the car. So what happens when it encounters this situation. So you can see it thinks there's a lorry. Now the lorry is sideways. Now there's a Jeep. So this is clearly an indication that the car doesn't know what it's doing. Now there's a pedestrian, working behind a lorry, and this is an actual production system. So you see, the point that I'm trying to make here is that these rare events are actually important, and of course it's not very likely like you're going to encounter them, but when you do, when these things kind of tend to have catastrophic consequences. So either, in this case, it was just bad publicity for Tesla, because everybody, I know this person shared this video online, and of course everybody was laughing at Tesla that they cannot drive. Of course, sometimes it can have more serious consequences when some objects are missed, and therefore the car doesn't know what it's doing. So let's take a look at how big this problem actually is. How rare are these events? So let's again stay with the example of a horse-drawn carriage, and let's stay local. Let's say in Czechia. What are chances that you would encounter such a horse-drawn carriage in Czechia, and more specifically, what is the ratio what is the chance that you will be actually involved in an accident. So fortunately, in our country, or unfortunately, depends how you look at it, we have a quite detailed database of all the accidents, all the traffic accidents, and if you look at it, then in 2021 there were actually 3 accidents involving a horse-drawn carriage in Czechia. There's a special category for this. Strážka s jedoucím nekolejovým vozidlem for Czech speakers. So yes, apparently there's a category for it, but you can see out of 100,000 accidents a year, this is actually a very small fraction. You may also argue that sometimes it wasn't even fault of the horse or the owner of the horse, if you like. In this case, it probably the car crashed into the carriage, and this is because the driver was drunk. So again, this is like further motivation in my view to support the fact that autonomous driving, autonomous cars will actually make our lives safer. So now that we know what is the sort of frequency of these things, of these events, I will just quickly skim through it. Let's just see how likely are we to have this particular instance in our training data set. So let's assume that this is quite a realistic scenario. You have some budget to create the training data, your Tesla or your Mercedes, Skoda, whatever, and you are trying to build a data set for your cars to train on, and you are given a fixed budget. So let's say you are given $1 million to create a training set. The obvious question is, like, what is the likelihood that this sort of rare events will be actually included in this data set? Because you may think, okay, $1 million is actually quite a lot of money. I would have hoped that there is at least that there's like a decent number of training data even for these like sporadic events. And if you do the math or estimation, if you like, we assume that we know the frequency, that's 1 in 100,000. We know how much there is in a video sequence, how many vehicles there are in a video sequence, what is the sort of rough rate labeling cost. You sort of very quickly arrive at an estimate that there's only about a 10% probability that after you had spent $1 million, there is 1 horse carriage included. So this sort of gives us, or this is sort of the intro for why we need or why this is a problem. And secondly, what is the main limiting factor? The main limiting factor is not that we don't have the data, because these days everything is recorded. Teslas, again, all the cars that are sort of out there, especially outside Europe, where the privacy laws are not as strict, they are constantly recording. So there's like terabytes of data available. The limiting factor is not the data; it's the fact that someone needs to be a human being, needs to label the data, and that is the most cost. This is where the costs come from, because if you want to label terabytes of data, you need billions of dollars, and obviously this is not feasible. So therefore, we are, not just us, but people are interested in methods which don't need labeled data, which is like a traditional approach in sort of machine learning or computer vision. You have your images or whatever data you're processing, you have your labels, and then you train the system for sort of mimic the labels, or to represent the labels as best as it can. So today I would like to talk about 2 sort of approaches how to handle the problem. One is called weak supervision, or transfer learning, if you like, where we don't have the data we don't have the labels for the specific task. We may have some pre-existing data labels that are used for different tasks, and we would like to use them to train our method without sort of collecting human labels. And the second approach I would like to talk about today is something which is referred to as a self-supervision, which is when we are using some internal consistency of the problem or some constraints of the problem to actually learn and train the method without any labels. So let me first talk about weak supervision. And I will talk about weak supervision in the context of 3D object detection in LiDAR. So this is one of the core problems in autonomous driving. You have LiDAR sensor, which is scanning constantly the surroundings of the vehicle that is moving. And of course, having a sensor is one thing, but then you need to make sure that you can actually detect different objects in the surroundings. So in this case, you want to detect cars, you want to detect them as bounding boxes, and you can see it's actually quite a challenging problem because the LiDAR is sparse, there can be reflections, there can be lots of noise, but at the same time, it's the key component in the video that I showed with the Tesla and horse carriage. This is actually, it's mostly based on LiDAR, and definitely, so having a method to train LiDAR detector is very important. At the same time, it's also very costly to train it because, again, you need, if you want to train LiDAR detector, you need to show people hundreds of thousands of scans like this, and someone needs to manually, or with maybe some help of some existing tool, they need to manually sort of create these 3D bounding boxes and say this is a car, this is a pedestrian, there's nothing there. And this is a very costly process. We may be talking maybe about $100 per single sort of scene like this. So the idea of our method is to use a consistency between camera and LiDAR, because typically in a car you have multiple sensors. So typically you have a camera that looks forward and maybe some other places, and then you have the LiDAR. And these two sensors are in sync, which means you can, for any given timestamp, you know what the LiDAR sees and what the camera sees. And we can also use an existing 2D detector, which is, again, a standard off-the-shelf tool these days, which already has very decent accuracy. And we would like to use this detector to actually create the training data for the LiDAR. The way we do this is I'm trying to show in this pipeline. What we do is we have a camera image on the left, and we are using an off-the-shelf detector as well as instant segmentation. So we have the mask of the object that is interesting to us, in our case cars. We are able, because we have the camera calibration, we are able to project this mask into a 3D point cloud, and basically combine or overlap, if you like, the LiDAR with the segmentation, which gives us something like this. So this is more challenging example, where on the right you can see sort of the camera that captured this image. This is the light. This is the scene that was captured by the LiDAR, and we are using the segmentation to sort of filter out the reflections in the LiDAR, which the camera has determined that it has it belongs to a car instance. The main challenge with this is that, of course, the match isn't precise. So there are reflections that in LiDAR which do not correspond to the car, and vice versa. Sometimes the LiDAR is missing some points. So it's a very, very noisy problem. And out of the box, it doesn't work. And our sort of innovation, or if you like, novelty, is that because everything's noisy, we actually make the network predict its own errors, or it's the noise. So for each point in the scene, we ask the network to do two things. We first ask the network to predict what is the distance between sorry, let me rephrase it. We have one thing I forgot to mention is that we, as a prior information, we have a rough shape of a generic car. So we know this is the yellow thing here. We have a we have a sort of prior knowledge of how a car may look in general. We have like a kind of a very generic shape, and we try to fit this generic shape into the point cloud, into the filtered point cloud, and this gives us some sort of error. It gives us like a fitting error, if you like, but because there are many outliers, as you can see, for instance, here in the back or here in the front, the guard rails, the network also needs to say, okay, well, I believe this point actually should be assigned to the car or to the model that we're trying to fit, or it should be discarded because it's an outlier. And the way we do this is we ask the network to actually predict its confidence. So this is like a sort of unsupervised way of making the network predict its errors. And this is done by using this following loss function. Again, I don't have time to go into detail here, but basically what happens is that for those points which are sort of far away from the car, the network can say, okay, I disregard those points. I will not consider the loss function or the distance between these red points and the car because they are clearly outliers. And the main novelty is that the network is actually learning not only to predict the position of the car, but also to predict what is the noise. And overall, just to show some empirical results, it seems to work reasonably well. There are some standard data sets that this method is tested on, and of course, it still cannot be compared to training with fully supervised methods. So compared to a situation when you have all the labels, but we are getting close. And we have actually one more work with my current student, which actually closes the gap even more. So this is not published work. I didn't want to include it here, but actually we are actually very close to closing the gap between the fully supervised and weakly supervised methods. So this is the first method I wanted to talk about. The second method in the remaining 8 minutes I would like to talk about is self-supervised methods, or it's a self-supervised method. In this case, this is just an example. So this is how the detector looks when it runs. So in the top you can see the camera image. In the bottom is the detectors. Are the detections that were automatically created without any human in the loop. So the second method I would like to talk about is self-supervised method. Again, the task is very sort of typical for autonomous driving. In some cars, I actually lied, there is no LiDAR, right? So if you buy today, if you go to a shop and you buy a new car today, the likelihood is that it's not going to have a LiDAR. So I'm talking of the likes of the latest Škoda Superb maybe, or things like that. It doesn't have a LiDAR, but it has a camera. It has a camera behind the rear view mirror, and we still want the car to sort of use the same, or to exploit the same benefits of these algorithms that work in 3D. And therefore, the crucial component of this autonomous driving problem, or the crucial component is something which is called monocular depth, which is a transformation, if just very simply, of an image from a single camera, typically, because there's only one camera. The manufacturers of cars, they tend to save money, so there's only one camera, and we want to create a depth map, which can then, of course, be transformed into a LiDAR or pseudo LiDAR, and then the whole story with reasoning in 3D works. So basically, we want to sort of compensate for the fact we don't have LiDAR. We want to create the 3D scene out of a single camera. So this is called a monocular depth. It's a problem that is being studied by many different people, by many different labs. By no means we are the only ones who's looking into it. And the original method by Goddard et al. Is called monodepth. The way it works, and I guess the beauty of the method is that it does not require any labels again. So it's self-supervised. It uses a consistency of a sequence. So because it's the data, of course, by like it's when you're driving, it's a moving sequence. And what is actually was actually very surprising at the time when they introduced this method is that this signal can be used to train this monocular depth. The way it works is that the method basically predicts from you take two subsequent images. So you have image at time t and a subsequent image at maybe 250 milliseconds later, and the car moves slightly in between these two images. And if you are able to get the position or the pose of the car correctly, and you are able to get the depth map of the image correctly, then you are able to transform or warp the image into the future. So you are basically saying, okay, let's say the network says, okay, the car moved by 2.5 meters, and this is the depth map, and therefore I can you can imagine that I can create or artificially generate an image which looks like it had moved by 2.5 meters, and I compare it. I have a loss function where I compare this sort of predicted image with the actual image in the sequence. And this signal, although it at first sight it seems it's very weak, is actually enough to train these networks. This is why it's called self-supervised, because there aren't any labels involved, because the network, when is trained from scratch, it learns to sort of gradually predict the pose as well as the depth map. And of course, when what we are interested in is not so much the pose estimation, but the ultimate result is just this top part, when we have a network which takes an image here and it outputs a depth map on the right. Our contribution to this method is based on an observation that this is a self-supervised method, and therefore it actually doesn't need any, as such, it doesn't need any training labels. But okay, the idea is that that there's some training, you train this method, but what stops us from sort of keep training the method when at inference time? So because again, there's nothing like typical methods, of course, you don't have any labels, so you're sort of only restricted to the most common pipeline when you have a model, you train the model, you deploy the model, and then everything is sort of fixed and the model somehow works. For self-supervised methods, actually, we pointed out that you can actually continue improving them even in production, because again, they don't need any labels. So we basically show or test that we train the method to the monodepth method as per usual, and then either for every image or image pair, we sort of run on the test set, or at inference time, we run a couple of iterations of the optimization, and we actually show that this gives us better results. So again, this might look slightly controversial, because typically you say you're training on the testing set, but in this case there aren't any labels, right? You can view this training as a pre-processing step, if you like. And of course, there are different ways how to approach this. You can do this for every image from scratch, or not from scratch, but from the pre-trained network, or you can do it in a sequence when you actually exploit the fact that when you're driving in a city, or one given city, maybe at the beginning you somehow don't know where you are, or the network it's kind of everything's new to it, but then of course the scene repeats itself. So as you're driving alone, the idea is that the algorithm and the weights will actually get better, because again, it's actually exactly like in the training time, we are using the consistency of the of the 2 subsequent frames to train the method. The main observation that we did is that actually, like, if you do it like sort of in a naive way and you train the whole network, then it doesn't work. What you need to do is you need to there are sort of 2 parts of the network. There's an decoder and encoder, and the key is to only update the encoders. So sort of the part of the network which sort of takes the image and generates some internal representation. Our sort of interpretation of this is that the decoder somehow stores like the shapes and the different like knowledge of the world that had to be trained, and it like needs to be very the training set needs to be very large to be able to train the decoder. Whereas when we are sort of updating the encoder with only like a couple of frames, or actually 2 frames in the first option, then we basically are just sort of making changes to the detection part of the network, if you like. So again, some empirical, some qualitative results or quantitative results, sorry. So again, we show that basically just by employing this simple trick, if you like, on running this pre-processing step on the data, we are able to consistently improve pretty much any sub-supervised method, because again, it's a principled way. When you don't require labels, then you are able to run or improve the method even during inference time. So here are some examples of our method, and I think I'm right on time. So I would like to just thank my collaborator. This was done with people with Robert, Eldar, and Andrea.